it is time to analyze the graph of a rational function. Now, we have been working with our rational functions. We're going to do a little more with it here today. And I think what many of us often like are some step-by-step guidelines, right? A lot of us are step-by-step type people. Not everybody. Some people like their life to be complete chaos. But a lot of us are step-by-step folks. So if you're a step-by-step folk, then I would jot down some of these steps to work step-by-step, which was an old show, step-by-step. You probably never heard of it, but it was a big deal back in the day. All righty. So first step, completely factor our rational function. We're going to call that r of x, okay? Find our domain. We're going to simplify this thing into its lowest terms, right? We're going to cancel some things out, find holes, all that good stuff. Then we're going to find our x and y intercepts, right? We want some points. We want some points to throw on the graph before we graph this thing, right? We want to locate our vertical asymptotes by setting the denominator equal to 0 and solving. We're going to use our multiplicity to determine the behavior of the graph around those vertical asymptotes. We're going to talk more about that in a little bit. We're going to locate horizontal or oblique asymptotes, okay? Determine if there's any kind of an intersection, right, with this asymptote, because it can cross a horizontal or an oblique asymptote, and then boom, we're going to graph this thing, right? Awesome. Asymptotes, holes, intercepts, that's the big deal right there, right? So if you want to jot this down, feel free to pause the video if you haven't done so already. Jot it down, hit play, and keep it moving and grooving. So when we're looking at our vertical asymptotes, as we talked about, depending on the multiplicity, right? If we're looking at our vertical asymptote, here it has a degree of 1 or an odd degree. What happens is as x approaches that asymptote, in this case it's x equals 0, as it approaches, it goes in opposite directions. Notice how from the left it's going to negative infinity and from the right it's going to positive infinity. But when the multiplicity is even, for example, in this one it's x squared, it's the degree of 2, they go the same direction. As it comes from the left, it's going to infinity, and as it comes from the right, it's going to positive infinity. Okay? So in general, what we can write down as a statement is it's an odd degree, then it will go in opposite directions. When it's an even degree, it's going to go in the same direction. All right? And these types of things can help us figure out different characteristics of either the graph itself based on a function or about the function based on the graph, okay? We can always do some test points around these asymptotes as we've been doing, but it can also help be like, wait, yeah, that does make sense, right? Because we make mistakes too. Like if I'm testing points and all of a sudden I get them going opposite directions when it's an even multiplicity, I know I did something wrong, okay? So always good to be able to attack this from multiple angles, math. Feel free to pause right now if you want to jot any of this down. If I move too fast, whatevs. So pause if you need. I think this is another lovely little graphic we have here. Really just putting some of the things together that we've been talking about, we've been working with, but more say like in an organized, like we're really talking about this right now. So we've done this in problems, but I think this could help organize your life a bit. So over on the left-hand side, as x approaches negative infinity, our function is approaching 0. Over on the right-hand side, as x approaches positive infinity, x is again approaching 0. And then we have how we would write our behavior around the asymptotes. As x approaches 0 from the right, that's what that little positive means, f of x is approaching infinity. And then as x approaches 0 from the left, that's what the little negative means, then f of x is approaching negative infinity. Okay? Obviously this changes for each graph, but a nice way of writing this down and what we're looking for at the asymptotes, both vertical and horizontal. Feel free to pause if you need to jot this down. Alrighty, so first example, we're going to do 2 examples here, and then there'll be a third one for you guys to try on your own. So we want to identify the asymptotes and or holes of the graph of the function if they exist, right? It doesn't always have to have all those parts. We want to graph the function and be sure to plot some points like our intercepts, holes, everything, right? We're putting that all down. And we've scaled this down a bit just to be so there's not so much written down, so we can combine some things like asymptotes all into one, holes, intercepts all into one spot, all right? Well, what's our first thing we're going to do here? Our first step, factor the entire function. So I have, I'll zoom in a little bit here. So I've got what multiplies the negative 3 and adds to 2. That'd be positive 3. and -1. So I currently have this large over small situation going on here with my degrees, right? So I'm always thinking about everything. So I'm thinking like, ooh, this might be an oblique asymptote here. I don't know. Well, once I factor this and now I simplify, well, first off, I'm going to jot down my domain. X such that x cannot equal 1. I don't want to forget to mention that. Well, that all cancels and I'm left with just this. That's my simplified function. So I have a hole at 1 comma something. How do I find that something? I can plug back into my simplified function here. So if I plug 1 and I get 4. Do I have a vertical asymptote? None. There's nothing left in the denominator there, right? I already know it's not a horizontal asymptote. We already said that because it's large over small. And then what about an oblique asymptote? Well, it reduces to a linear equation, right? It reduces down to a linear, so there's actually no oblique either. The heck? And maybe I'll use a few extra letters. Maybe, there we go. Okay. Or wait, how about instead of that, label it in the same fashion as all the other ones? Come on, Mr. Allen, get your life together. Get your life together. So what the heck is happening here? Well, let's keep cruising, then maybe we'll figure this out. Intercepts. How about my intercepts? I can do those, right? So if I want to figure out my x-intercept, I'd set the equation equal to 0, right? Because on my x-axis, my y value is 0. So if I set this all equal to 0, that'd be 0 equals x plus 3. I'd get x equals -3. So x-intercept would be -3 comma 0. And how about my y-intercept? Well, for my y-intercept, I substitute 0 in for x. So I'd have y equals 0 plus 3. So that would be 0 comma 3. Right? Because on my y-axis, my x value is 0. Wonderful. Fantastic. Excellent. So I've got some great stuff here about this graph. Let's pop this onto the graph and see if we can figure out what the heck's going on here with this no vertical, no horizontal, no oblique asymptote situation we've never seen before in this class. All right, so I've zoomed back out here. Let's get this on the graph. I'm gonna stay green because I'm feeling green today. Let's see here. So I've got a hole at 1, 4. I've got -3. So I'm gonna go with my x first. 1, 2, 3. There's my x-intercept. My y-intercept is 0, 3, 1, 2, 3. Okay. I have a hole at 1, 4. And now I'm gonna go ahead with my ruler here and see if I can pop that guy on there and connect everything. So this is really just, again, it looks like a linear equation. Because it's x plus 3. We know x plus 3 is just going to be like y equals mx plus b, right? It's just a straight line. However, because it was originally in that rational, right, the irrational form, we canceled that out. That's a hole there. It doesn't have any asymptote, so it looks like a line. If you were to graph this in your calculator, it would look exactly like the line y equals x plus 3 because your TI-84s don't show the holes there, right? It would, in your table of values, it would come up as an error at 1, but you wouldn't see it on the graph. It would just look like a line. Well, there we go. How about my, let's see, how about my range, actually? Let's toss my range in here. I'll do it right here. Range, since I got my domain, will be y such that, well, my y values, the only thing I have to eliminate here would be the 4. It's a positive 4. Cool. I like it. So we did a little more than what it asked for, but yeah, we got our domain, we got our range. This is a different situation. We haven't seen one of these before, so it's nice to get that one in the books. Feel free to pause it if you need to jot anything down that you may not have had time for. If you're ever not scaling these like I have here, make sure that you label your points. Like this would be 1, 4. This would be, like if I didn't scale it out, this would be 0, 3, and this would be -3, 0. I scaled it out, so we're good. But if you just plotted those and you didn't put the little tick marks, you would need to jot that down as well. All right, let's move on. All right. Ooh, kick the desk. Sorry. So we want to, again, same deal, asymptotes, holes, all that stuff. What's the first thing we're going to do here? I'm going to factor. It's my favorite thing to do, so I'm going to do it first. Factoring starts with the F, so factor first. All good things here, right? I'm going to go with a little purple here. I think that'd be nice. That'd be lovely. So if I factor the, whoa, what the heck is this? We got 4 terms. This isn't some normal, quadratic or trinomial. I'm going to have to factor by grouping. So I'm going to group the first 2 and the last 2, and I'm going to pull out some GCFs, okay? So I've got, I can pull out an x squared in the first one, and I'm left with 2x minus 1. I'm going to zoom in a little bit here. And then in the second one, I'll pull out, let's go with a negative 1. Because I can't pull out a 2 from the 1 there. And I'm left with just 2x, and then this changes to negative 1. Okay. We will have to continue with that. So that, I'm just going to, I'll go like this. We'll work across this way. So now I'm going to have x squared minus 1, not x squared minus 1, and then 2x minus 1. And then lastly, that's a difference of squares there. So I have x minus 1, x plus 1, and then 2x minus 1. Okay, lovely. That one had some steps to it. Now this denominator here is just x plus 2, x minus 1, isn't it? Multiplies to 2, sorry, plus 1. Multiplies to 2, adds to 3. X plus 2 and x plus 1 do that. I'm going to go ahead all the way over here. X plus 2, x plus 1. Now, I need to simplify if possible. Well, I can see that my x plus 1s will cancel. What does that tell me? That tells me that there is a hole in this graph at negative 1 comma something. So over here in the holes, I'm going to put negative 1 comma I don't know. Okay? How do I figure that out? Well, I could plug back in, right? I could plug in negative 1. So why don't we go ahead and do that? Let's. Let's rewrite our function here. Now that it's simplified, I have x minus 1, and then I have 2x minus 1 over x plus 2. And you know what I'm also going to do? I'm going to FOIL the numerator back together. So I'm going to say that we got 2x squared, and then I'd have negative 2x and negative 1x would be negative 3x plus 1 all over x plus 2. I think that both of these are going to come in handy in this problem, okay? So when I'm figuring out the whole, so maybe I'll box these. These are important to me. When I'm figuring out the whole, I would plug back in, right? Either one's fine here. I'm plugging in negative 1. So you know what I'll do is I'm going to plug in negative 1 to this top one here to figure out the coordinates of the whole. I'll do that in orange since I canceled out in orange. So I'm going to have negative 1 minus 1, 2 times negative 1, oops, and then minus 1 over negative 1 plus 2. And if I go ahead and evaluate that, that's going to be negative 2. This one right here is negative 2 minus 1 is negative 3. And down here I have 1. So I have negative 2 times negative 3 is 6 over 1. So it looks like 6 would be my y coordinate. So pop back over here. 6 is my y coordinate. Lovely. I like it. Fantastic. Wonderful. Okay, so again, we've got these two simplified forms here. Maybe before I continue and forget, I'll jot down my domain here, which would be x cannot equal negative 2 and negative 1. Domain is x such that x cannot equal negative 2 and negative 1. We'll have maybe our range a little bit later. We'll see. We may or may not do that one. I don't know. We'll see how we're feeling at the end. We'll see where we're at. But I'll save a spot for it. Okay, cool. So now what? Where do we go from here? How about our asymptotes? Do we have any asymptotes here? Let's look at that. Well, I do have something left in the denominator. I have x plus 2 left in the denominator. So that means my asymptote is x equals, so my vertical asymptote is x equals -2. How about a horizontal asymptote? Well, my degree in the numerator is larger than the denominator, so that would be none. But then I have an oblique asymptote, right? We got to check for that. Well, in this case, it didn't like all divide out down to just a linear function at the end, so I do have to figure out my oblique asymptote. Now, lucky for us, and here's why I did this. In this form, I now have a denominator that is a linear binomial. I can use synthetic division. I could do long division with my original, but why would I do that? When I factored, I canceled. Let's use that to our advantage. I'm going to do some synthetic division. So I will throw in, and I'll do this in another color just because that's fun. I'm going to throw -2 in the box, and then I've got 2, -3, and 1. And then I will do some synthetic division. So I'll drop the 2, and then I got -4, add them, I get -7, multiply, I get 14, so then my remainder is 15, which I really don't care about, right? That's just my remainder. I'm not using that in this situation. All I'm using is that this is going to be my coefficient of my linear term, and this is my constant. So 2x minus 7, y equals 2x minus 7. That is my oblique asymptote. Let's jot that down back in my original, or my more organized work over here. So that's y equals 2x minus 7. I love it. We're getting somewhere. So we got all of our asymptotes taken care of. How about my intercepts, right? My intercepts are the next thing to do. So again, I'm going to do some side work over here. So I think that it's keeping things a little less cluttered. So my intercepts, let's go with my x-intercepts. I'll do a different color again. Let's say, so if I want my x-intercepts, I would set my function equal to 0, right? Because my y value would be 0. And the only way I'm going to get this to equal 0 is if my numerator is equal to 0. Right? My denominator cannot be 0. Okay, so -2 is not cool. All right, that's a vertical asymptote. But here, if I got x to equal 1, or I can get x to equal, I would add 1 divided by 2, that'd be 1/2. So my x-intercepts are 1 and 1/2. So let's jot those down in our main work. So 1, 0 and 1/2, 0. X-intercepts 1, 0 and then 1/2, 0. All right, how about our y-intercepts? Well, what do I do to get my y-intercepts? My y-intercepts, I need to substitute in 0 for x. And that's actually easiest to do in either the original function or a non-factored function, because I can just look at my two constants, right? Because all these are going to cancel out if I put in 0. I'm going to get 1/2, right? And that would hold true in this original as well, where I have 1 and 2 as my constants. So I'm going to get 0, 1/2. It's not like it's always going to work out this way where these are opposites of each other where they're switched. That's coincidence, okay? It could be different in any one of these functions here, okay? So we got a whole lot of information here. I think now it's time that we actually we graph this thing. Let's do it. I've got a lot here. So let's see. We've got I like to set up my asymptotes first. I'm gonna do asymptotes in a different color. I'm gonna go with let's go with how about light green? That sounds lovely. So I've got y equals 2x minus 7, and I've got the -2. And I'm gonna throw some I'm gonna throw a few tick marks on here. I'm going to pause the video real quick. All right, here we go. So it starts at -7 for my y-intercept. So I have 1, 2, 3, 4, 5, 6, -7. And then I'm going up 2 over 1. Awesome. Up 2 over 1. Cool. And I'm going to go with my ruler here. Woo woo. That looks pretty darn good. There's my oblique asymptote. I like it. Cool, awesome, fantastic. Let's see here. How about my vertical asymptote? It's at x equals -2. So I'm just actually going to pop that ruler back out, throw a 90 on that so it's vertical. Boom, I like it. Lovely. Cool. Awesome. Wonderful. I'm going to go back to my purple marker for the rest of the graph. So I've got my asymptotes. I have a hole at -1, 6. So 1, 2, 3, 4, 5, 6. Don't want to forget to plot that. I have an x-intercept at 1, 0 and 1/2, 0. That is really difficult to do right there. And then I have, I'm going to zoom in actually. Why don't I do that? And then I have a y-intercept at 0, 1/2. Okay, so a whole lot crunched together right there. And let's see here. So this graph is going to look something like this. So it is going to dip below and then pop back up, and then it's going to eventually it's going to approach that horizontal, or sorry, that oblique asymptote, but never quite get there. So that's that section. And we know, since it's the odd multiplicity in the denominator, that our other portion of the graph would be down here, doing that same thing where it like mirrors over. Okay, we're not gonna talk about the range on this one, because this is really a lot of information right here already. Okay, so if you didn't make the tick marks like I did, we would be expecting you to label the points like these right here. We'd be expecting you to toss those on the graph and labeling the ordered pairs so we can clearly see where they are. If you scale it out, that works as well. Okay, so as long as it's clear. As long as it's clear, that's what we want. So let's think here. There is one last piece of information I'd like to chat about. You know, we were all chatting as pre-calcers, and we're like, you know, what's really going on? Like, do the students understand what the heck's going on? Why is this graph getting infinitely closer to this this line here, but never quite gets there? Like, what's actually happening? Okay, what is actually happening? So I'm going to pop over to this here. Remember how we said that this remainder didn't really matter, right? It doesn't matter for the purpose of getting the oblique asymptote, but what's actually happening? Well, when we divide this all out, and this is a sidebar here. This is some fun information. I'm gonna go with this blue color. So when we divide this all out, what we're really left with is this: 2x minus 7 plus, and then it's 15 over x plus 2, what we were dividing by, right? This right here is equivalent to our simplified form of our rational function. This right here is this written differently, right? They are numerically equivalent. They will graph the same, okay? So what's really happening? Well, if I plug in numbers, right? So if I plug in numbers, as I get larger and larger, what's occurring? Well, as I get larger and larger, I want you guys to focus on this portion right here. This guy right here. What's happening as I get larger and larger and larger and larger numbers? Well, as I plug in, say, 100, 1,000, 5,000, 10,000, a million, this denominator is getting really, really, really big. And what's the same number divided by a bigger and bigger and bigger number? Well, as x approaches infinity, meaning as x gets larger and larger and larger, this is going to get really, really close to 0. Close to 0, right? Never quite get there, but infinitely closer to a value of 0. 15 divided by 1,000,000 is real close to 0, but 15 divided by 2,000,000 is even closer to 0. So as I'm adding a number, so this right here is an equation of a line, right? This is y equals 2x minus 7. As I add a number that's infinitely closer and closer and closer to 0 to this equation, it starts to look exactly like this equation, and it will look like this line, right? If I add a really, really small number, it's still going to look pretty much like this right here. 2x minus 7.00001. You're going to look a lot like 2x minus 7. So that's why as we get larger and larger and larger, this starts to become almost this asymptote. It follows along with this asymptote and flattens out and starts to look like that line. It never is, but it gets infinitely closer and closer and closer. It starts to look like that oblique asymptote as you go further out, as you approach infinity with your x values. Okay? And the same would go with our negative values as well. So I think it's something that we often overlook, and we just remember these tricks and things like that of like, oh, we just do this and we do that and we divide out and then we forget about that and we do this. Whoop. We don't really know what's going on. So I think that's kind of an interesting way of looking at it. looking as we get larger and larger and larger numbers, what's going to happen, okay? So, and I think that's a concept that's really nice to take with you into calculus as well. What's happening if we start just plugging in numbers? Let's just see what happens, okay? Don't remember tricks. Let's just see what happens and see what we can do with that. All right, I think that's pretty fantastic stuff right there. I think the only other thing that I'd like to address here, guys, would be some of our end behavior. So end behavior, a little bonus math. So as x approaches negative infinity, what's f of x doing? Well, as x goes to negative infinity, that's this portion of the graph, it's going to negative infinity as well. And then as x approaches positive infinity, meaning as we go to the right, while that graph is going up, that means that f of x is approaching positive infinity. And then how about behavior around the asymptotes? So let's see here, as x approaches negative 2 from the left, it's going to negative infinity. So as x approaches negative 2 from the left, f of x is approaching negative infinity. And then as x approaches negative 2 from the right, forgot my commas, f of x is approaching positive infinity, right? It's going up. And that makes sense that they're approaching different. They're going opposite directions because our denominator was left over with x plus 2 to the first power. If it was squared, they'd be going in the same direction. But that's not the case on this one. I think that's enough information here. That was great. That was fantastic, wonderful. I hope you guys all enjoyed it. America, freedom, rock and roll, Costco, water stain. Boop. All right, you guys have a fantastic day. See you in class.